Well, I know that the first talk after lunch is always the most difficult one. I'll try to take you awake, speculate a bit on what we could do. Okay, immunologists every day face a question, clinical, and they have the question of which is the best time and dose for a certain therapeutic agent to be administered to the patients to decrease or eradicate a pathological condition. To help doctors in this kind of efforts, national health authorities usually provide clinical practice guidelines based on the paradigms of the evidence-based medicine. They just go on the website, they have a lot of this for each authority. They have what to do. Do it this way and you will be safe from any legal problem and other questions. Well, the question we try to discuss now is what can do modelers to help medical doctors in solving this task. Optimal control theory is, and that's what we will discuss in this, we'll try to discuss in this talk, is the attempt to apply a technique which is widely used by industrial engineers. It's a technique which is based on a wide range of maths engineering, and which is called the control theory and the operational research. Any engineers knows very well what's going on with this, because they do apply everywhere. In any apparatus they build up, they have control, the optimal control. Starting from the simple washing machine to the aircraft. I mean, they do it in very complex systems. Okay, the plan of this talk would be just a brief introduction to control, the optimal control, the model prototype cycle in the industry, the analogy and differences between industrial apparatus and living bodies, and then discuss two examples just to show what is the major difference, you know. Okay, a control system, it's an apparatus, it's a device that regulates the behavior of the system. But of course, to have a control system, you must have a system to control, okay, and a model of the system to build up your control system. Then you have to decide what you want to control. So control policy. Okay, on an aircraft you can decide to control the route, okay, or in a car you can control the fuel consumption and things like that. And then controller units. So a device which then modify the inputs of the apparatus just to get to the goal. Control system may include a feedback. So a sensor, so you have a sensor which measures the system outputs, so how the system reacts to the control, and then cycle adjust inputs so to get to the final results. The most simple one, control system, is an open loop. You have a desire response, a controller, input process on the system and output process. Simple. I mean, you have to control that decide at some time your system has to switch on, and after a certain time it has to switch off. Simple as that, the simple case. More complex closed loop, as I told before. You have a controller, a system, and then you have a sensor which measures, and now when we see difference with living bodies, there's a sensor which measures the output of the system. And this is a feedback, and feedback goes to the controller, and the controller adjusts the inputs, so to go to the desired outputs. Aircrafts, of course, I mean, they have to follow routes, and of course they measure how far, if they are on the route, if they move from the route, for the wind, for instance. They adjust the input so they keep the road. Controller on boats. They say the target where they have to go, they fix the way, but of course the environment, I mean the wind can move the boat, so they adjust it on the output, on the position. Simple control system consider control one signal input and one signal outputs. Those are simple case, but there are more complex ones. We have multiple inputs and multiple outputs. The example here is rather complicated if you, if you know large telescope now, there are a collection of mirrors which rotates, and they have to control the images. But while they rotate, there is a stretch which change the shape of the mirror, and also there's a turbulence which change images. So they have a complex control to adjust the images while they follow the star on the sky. Well, it's done. They do it. The engineers, they do it. They're very clever. They do it very well. So just to summarize, I mean, that's to set up a controller, we must identify the controller goal. To develop a model of the system. To check the model correctness, of course. The model must represent the system. And then apply a controller, which is apply the inputs to this model to get the desired output, usually output after a certain time. I mean, there's not immediate reaction. Well, of course, engineers then go to the field test. So once they have built up the controller, they take a prototype or a real system, add the device, okay, measure the achievements of the control policy. If the achievement is okay, they're satisfied. If not, there's something wrong. Simply, there's something wrong. So they go back and say, what is wrong? Is wrong the input or is wrong the model? Maybe the model is not correct. So adjust the model, adjust the input, and then perform again the experiment. They do on prototypes, but at the end, they do on the real system. Of course, talking about aircraft, they establish prototypes. but at the end they test on the real prototype aircraft. There will be no passenger on top of that when they test it, of course. There's only one person, but they have to do it. So what we need, a system can be simple one, it can be a complex one. Air dryer is a simple system, but if we talk aircraft or a car, it's not a simple system. So we need to have a model of this system, which is a mathematical or computational representation of the system, in which they describe the outputs of the real system as a function of input. And then they have to collect a set of control functions in order to achieve the control policy. And of course a control policy. A mathematical model is a description of a system using mathematical concepts. There are many ways to do that. There are ways in which you describe the components of the systems in detail, so you represent with equations. Or there are other models that engineers use in which they have simple metrics in which they adjust the parameters of the matrix and they have input outputs. The mathematical model most used are all the differential equations, of course, in which there is a lot of, in which we know mostly everything. Well, mostly, not everything. But if the system is too complex, ODE may become too complex too. And then all the power of mathematics, which is qualitative solutions, asymptotic, or whatever is in mathematics, I don't know going to bother you about that, cannot be easily used. Or maybe the representation with differential equation is too complex. So one can resort to other approach, which is have direct computational models. So you plug the system in a computer and then you simulate on the computer. The example that Francesco showed you at the beginning, first lecture, was agent-based as an example of this one. Okay, an example of mathematical models, not a simple one. So you have a set of parameters, which are the variables which describe the system, a set of inputs, a series of functions describe the inputs, and then you have a system of differential equations which describe. As I told you before, it's the drawback of this representation is that to keep the system of all the differential equations tractable, I mean, you can treat it analytically, the number of differential equations cannot be too high. No? Unless, of course, you have a large system of differential equation, and then you have to solve it numerically, of course. Have no chance to have analytical solutions. And then you have to this control function. The control function tries to control the system. So the equation to controller can be set on this to say, okay, given the system described by the sets of differential equations, find the function u such that the values of the output of the system, the values of the state variables of the system, reach a fixed value at a time t greater than the fixed time tf, the final value. However, this problem has not a unique solution, and this is very simple to understand. I mean, we don't need mathematics for that, but the experience. If I want to say, okay, how should I need to push my engine to go from one point to the other one in a fixed time, I can decide to go fast first and then to slow down. I can decide to go at intermediate speed. I can decide to go slow first and then go fast. I can decide to go like a wave-like, accelerate, decelerate. I mean, there are many possibilities to get that. So this does not solve the problem of the optimal control. So to find an optimal control, we have to add something more. What we have to add? We have to have what is called a cost function, okay, which includes sometimes some constraints, and find the solution of the control variables which minimize the cost function. Again, an example means, okay, I have to go from point A with point B with the car. I want to find the best way, which minimal fuel consumption and minimal time. Of course, I have constraints. I cannot break the one-way routes on the roads. I cannot overcome speed limits. So all this comes in your model to the optimal control. And once you get that, then you go in the library and you have shelves of optimal control theory and decide what you have to apply. In many cases, there are already software done. MATLAB has it, mathematics has it. I mean, engineers now, they don't solve it directly, they use these tools. But in any case, the last step is the field test. So they do it, they do the theoretical spec, they build up the device, and they have the field test. And the field test means that if it's okay, if it fails, if in reality, which is often happen, okay, I must say every time, of course, when they do that, they look back and say, okay, adjust our controller because it does not work in practice. Okay, that's what engineers does. Okay, let's try to say, can we translate this experience on living systems? That's the goal. The system, what is the system in our case? It's the human body, it's an organ, a pathology, and of course, here we have to include the immune system. The control, what's the control function? The drugs, the protocols, of course the effect of the drugs, different drugs. What the control policy? Well, with living people of society to have a pathology-free organ health state. Okay. Or do we not really want to have a pathology, control policy, let this guy die, which would be unfair. And the biology, cost function to minimize. Here the biology and medical doctors come in. They can ask to minimize the number of administrations, to minimize the dosage, to control the toxicity of the drugs. They have to do the requirements, of course. On those requirements, we can try to build up. And of course, we have we need a good model of the system. Here comes the difficult part of the game. Do we have a good model of the system? We really don't have. We can only approximate the game. Okay? But of course, we try to have good models of the system. We try to describe the immune system in many ways, and of course, the description can be as simple as possible. We'll never include everything. Forget it. We'll try to include what is necessary to describe the system in a proper way. Control functions. Okay, that's much easier. We know the drugs. We should, underquote, know the effect of the drugs. In some cases, we don't really know exactly what the drugs does. Okay, we should do. We can say, okay, control the dosage, control the time in which we administrate the drugs. We know the viral load. We know the tumor cell concentration. Well, we can expect to know something about that. And then we have the control policy, and again, the cost function to minimize. I will assume we have done it. What is the field test for us? Well, the field test, there is no way, is the experiment. Any model without experiment is useless. It's a video game. Well, first time I said this, Francesco, when I said, he said, "Oh, you're not joking." I thought, it's a video game. If you not check the model with the experiment, it's a nice video game. I have nothing against video games, of course, but that's not science. What's on the market? There are a lot of papers on optimal controls, mostly done by mathematicians, which like to play. We have done a lot of work, but very few of them. They come from philosophy. Okay, I know this technique. I can have a model. I can build up a control, optimal control, using the theory, 14, the max principle, or whatever it is. Okay? But at the end, there is no test field. At the end, there is no test field. Most of those models are based on ODEs. I have nothing against ODEs. They're very useful in some situations. Okay, if the system can be described by ODEs, God save us, it's okay. It's nice. Very few tests in vivo, but someone has already done a market on that. I mean, probably you know. I mean, Sphere with Optimata, they have it on the market. The virtual patients. I mean, they do chemotherapy, I guess. They have this great model of cancer growth, and they've done it. They do it. I mean, I don't know how much they sell it, but Optimata is on the market since 10 years, something like that, more or less. So they must get some money for that. Otherwise, they wouldn't stay on the market 10 years.
So your say is next time we see a paper like that, reject it?
Sorry?
Your claim is next time you see a paper with no validation, reject it?
Okay. I will show out two examples to explain it to the two opposite situations. I'm not going to I have no data on software by sphere. I mean, the first one shows mathematical procedures to optimize both timing and dosage, considering multi-therapies. And the second one is the experience we have done with Francesco and a colleague in biology. Okay, the first one, which is, I choose one of these. It's done by Castiglione, Piccoli, and Cappuccio, with the young guys. Benedetto Piccoli is a mathematician expert in control theory. So they've done this, and they found these very nice series of papers on optical control in immunotherapies, okay, which is a general approach. And then they give an example of the general approach using a model of tumor growth and interaction of tumors with the immune system, which is a model which is on the market since '98. It's a well-known Kirchner-Panetta model. And they consider two types of treatments. Immunotherapies, two immunotherapies using cytotoxic T cells, CDL, and interleukin 2. Again, what they need, what they use, it's a model of the system, a control function. The nice of this paper is that usually when they do with the control function, they consider continuous functions. So that means you give drugs in a continuous way. They managed to adopt this procedure to have with the delta functions. I mean, in simple terms, I give a tablet. I give a tablet to you. That's so, give you one drug and that's it. And they control the total quantity of drug administered. And the cost function, they did consider some clinical requirements, the final tumor mass. There's a control function to limit the tumor mass during the treatment. So they try to say that tumor mass cannot grow up to a certain level during the treatment. The total amount of drugs applied during the treatments, and what is called the drug holiday. So there's you cannot supply drug every time, at all time, because there's a doctor saying, okay, you have to do some rest. You cannot take drugs every day. And the goal of the therapy was tumor mass reduction with minimum number and quantity of drug administrations. I'm not going through the maths. I mean, that would be extremely boring after lunch. It will be extremely boring for all of you. Just show that the model they use is simply the simple model which considers concentration of effector cells, concentration of tumor cells, and concentration of interleukins. And they are linked on this picture which is down there, okay, in which effector cells kill the tumors and things, and other things. Decay rates, I mean, you can look at the equation, I mean, concentration, the tumors grow with kind of logistic equations, but the number of tumors are decreased by the effector cells, things like that. And formalize a multi-therapeutic protocol, control function, in which you administrate either one single or two therapies, and the cost function to optimize with the four terms which I just described before. The final tumor mass, the integrated cost of max exceeding a threshold, the cost associated to the drug delivered, and there's a cost associated to the interval between the two following inoculations. And when you have multiple criteria optimization, you have to decide a weight between the different criteria. Say, which is more important between these criteria? And this is decision, arbitrary decision. Simply, it's arbitrary. So again, for this, if you do this with the doctors, and then the doctors say, this is more important than that, or the other. So you adjust the weights so to follow, okay, you can change it and then try in another case. In their favor, they say, okay, we set everything to 1, equally. There are no weights, preference weights. And then, of course, they have this, at the end, they sort it out numerically. They consider a treatment only with cytotoxic cells, a treatment only with interleukin 12, and the combined treatment with 2 of them. But the drugs were administered at the same time. They don't separate the times. And the results was when they control with cytotoxic cells, that was okay, but you see this straight line over there is the threshold which should not be overcome. So a single treatment is not enough. Well, if they do with interleukin, just forget it, they overcome everything. But combining the two, and the third one, they manage to stay under the threshold and to control the tumor mass.
So is this real data?
No.
Or
This is just mathematical speculation. This is a mathematical speculation. It's a pure mathematical failure.
I understand.
It's nice piece of mathematical work. It's nice work. It's something that in principle can be transferred, so they have to test it in the real data, which is, of course, they haven't done it, because they have to find someone who say, okay, let's try to have control done on this way.
Real mice.
Wait. You need a biologist to you need a biologist who wants to do that. I mean, Castiglione, Piccoli, and the other guys, Cappuccio, they work in CNR, but they work in applied maths institutes. They really, Benedetto Piccoli is applied maths, Filippo Castiglione is computer scientist, and the other one I think is a physicist, who spent, by the way, spent here with Tzvi in Israel. Okay. Now, okay, the model they use is simple, and this model represents one person or one mice, I mean, and which is a mean mice. Let's say it's a mean mice. It's a median. There's no, how can you do with ODE to represent biological diversity? Well, with ODE it can be difficult, you should switch to another mathematical technique. You should insert stochasticity. You have stochastical ODE. But then the game, even mathematically, has become a bit harder. Maybe a bit more than a bit. Because then you have stochastic differential equations. Okay, the other experience, it's the other way around. It's the other way around because it was the biology who came to us and say, okay, I got this problem, and I want to help me in solving. So it's completely opposite approach, and that's happened, well, how many, 10 years ago? More or less? Yeah, also. And the guy who is involved in that is an immunologist, is biology doing immunology in Bologna, which is Professor Lollini. And he came and say, okay, I got a vaccine, an immunopreventive vaccine for mammary carcinoma, tested on mice. And on mice, this vaccine works. It works if I have a chronic protocol. But I don't care about the mammary carcinoma mice, but I care a woman. To translate into humans, I need to reduce the number of drug administration, because be an immunopreventive vaccine, you should say to a woman which is healthy, okay, come and take the vaccine. And that's, he says to me, they don't come to do the test controls, they will come to have the vaccine, they just will not come. So we have to find somebody which is the minimal administrations. Okay, so that was the question. And they say, okay, so it was the reduction of the number of vaccine administration. And of course, when we start to talk and say, what about the quantity of vaccine to administrate? And the answer was, I tested already. It doesn't change too much. It's more or less the same. It's not, which is sensible because the vaccine stimulates the immune system. So it's the stimulus which is irrelevant. You must give enough vaccine to stimulate. But if you decrease the vaccine, it's not that much difference. And the goal was on mice to prevent the carcinoma in situ, because you give the vaccine when the mice, you know that have the cancer cells, but they don't have the carcinoma in situ. So these people spend every 2 weeks, I guess, I remember, tested the mammary glands of the mice and check if they had the carcinoma by hands, but simple by hands. Of course, the vaccine was administered by intraperitoneal. Sometimes they kill mice doing injections, of course. Okay, that's the kind of vaccine they had it. It's combined 3 stimulus, the antigen, P1A5, the allogenic MHC, and interleukin 12. The mice, only they used for the experiment transgenic mice, which develop multifocal carcinoma about 20 weeks of age. The weeks 33, all carcinoma palpable in all 10 mammary glands. And the experiment they had before it was okay. They have a chronicle protocol which is cycle of 4 weeks. 2 weeks of the vaccine administration, 2 weeks of rest, and then repeat that. 2 weeks of vaccine administration, and every week we have 2 vaccine administrations. On Tuesday and Friday, Tuesday and Friday, if I remember properly. Only 2 of them because they decided to use the fresh-made vaccine. They said they don't want to have. And results for their experiment, if they use a chronic protocol, they need to repeat that for about 1 year. This is a couple of May. All 100% of the mice did not form a carcinoma in situ. But if, okay, this is the control, if they use start to early vaccination, we start early vaccination. So at the beginning of 6 weeks of age, they have early vaccination, which is a cycle of vaccination repeated for a short time. Then there was no formation of cancer. That after a while, the carcinoma in situ show-ups. If they start the vaccination late, situation was worse. I mean, that was late one, that was very late. The very late was more or less like no vaccine. So it was too late to control. So question is that redundant?
So you have 3 minutes.
Okay. Oh, that's insufficient. Okay. Okay, the model we built up was an ABM model. Skip that because Francesco told you about. And then, of course, we built up with Pierluigi the map of what's going on with this vaccine. And we reproduce the in vivo experiment. Again, the model we built up is works for one mice, but we could mimic diversity, biological diversity, playing on random numbers. So when we do the experiments, the in silico experiments, we run it to 100 mice. And once we have done it, okay, we were ready to check for all different protocols. But you cannot run all possible protocols because that's what, even on computers, takes too long. And when I say too long, it means that to run all possible protocols would take about 10 to the 17 times the age of the universe. So it's just forget even on a computer. But all possible protocols in 1 year for treatment were lost. Okay, and then we worked out that. And then, of course, we use a genetic algorithm to do the optimal. And we said, okay, that's what we expect with our genetic protocol. So we can do the experiment. We have done, Pierluigi has done the in vivo experiment on our protocols. So in doing that, he said, okay, I will do the in vivo experiment. So that's the genetic protocol comes out to be not uniformly distributed, the administration. So it comes and the immunologist say, how would you distribute the protocol with the same number of administrations? And this process, okay, I would equally distribute it and design an equal distribution. And so we test also that. Not we, they test. I've just seen the mice once, and that was my. Okay, so we test it, and what we discover in a simple way. Okay, we discover that the genetic protocol did work like the early one was not good on the survival side, But, funny to say, it was very good to control tumor multiplicity in different mammary glands. So this would be necessary. It was quite good to control the antibody levels. And when we discovered that, we checked something, and we discovered that what was not in the model was not taken into account of the aging of the immune system. The aging of the immune system was not taken into account. So, as I told you, now I was ready for the feedback. Doesn't work in vivo? Okay, we're ready for the feedback. Go, change the model, and adjust it. But even that, so we said that we confirmed that the chronic is redundant, of course, but even the plot model is not satisfying, the optimal one we get. And we find that aging should be added. Now, let's close my few slides. Okay, but every model we do, we can think about populations. Okay? Can we move from optimal control on population on personalized therapy? That's the question. Well, forget to have a model of a single person. That's too hard. But what we do, what we usually do, doctors, they classify patients in clusters. So we can have a model for a cluster of patients. Then we can say, okay, we apply the model of a cluster for single patients. I can measure the outputs. And from the output, I come back to control, feedback, and adjust the model. Just the model, and then run again, and then run again. In this way, we can try to do it. So this kind.
We have to.
Okay, that's it.
Okay.
So thanks for
Very
everything.
interesting talk. Okay, so I didn't rush the previous speaker to give myself more time, in case you thought so. And so you can see there are two red arrows, and those are the things I want to conclude with. So basically, I am interested in production of T cells prior to the issues that have been discussed during this conference. And there are two things that interest me. One is the very rapid expansion in the first stage. And the second, which is even more my favorite topic, is when is the decision to go into the T cell lineage final? Because they can sneak out and become B cells. The tools that will be employed will be mostly deterministic ones, unfortunately, but we are working on single cell stuff as well. And so this is the lineage commitment landscape. It's a cartoon, it's more complicated than that. I just want to convey where I'm coming from. So my previous waterholes have been the embryonic stem cell key players and issues related to whether they commit or not commit, and do they commit spontaneously or do they need external forces. Similar questions I have addressed for when you switch between red and white, basically, and it's only recently that I got into the T-cell community. Actually, this is my first conference on any T-cell people. So this is part of hematopoiesis. As I mentioned, I've been working on erythrocytes and neutrophils, and you have a decision here. And deciding factors are the GATA community, GATA1 and GATA2, and for the red blood, and you have P1 and CBP alpha for the other trait. And very interesting here has been that if you have EPO on We all know EPO from sports community. That forces the decision. But it turns out, actually, when we have investigated data, which is at a single cell level, we'll know EPO, that progenitor, CMP, will nevertheless spontaneously commit. So the role EPO has is basically, the way we interpret it, is to fertilize the proliferation. So if we go to today's talk, it's a little dissimilar because it's a single trail. And again, there are internal factors. It's GATA3, TCF1, BCL11B, and the correspondence to EPO in red blood cell production is the Notch signaling pathway. So, the early T cell progenitors. So, studying T cell production will, in a sense, be much easier than studying red cell production when it comes to commitment, because it happens at one place, whereas the other cell components, they are produced all over. So this is actually, if there's something to be learned here that can be used for the other lineages, it's fantastic. So 50 progenitors on the average enter thymus per day. It's not a lot from the bone marrow, and out comes, and one can debate that number, 10 to the 6 or something like that, immature or mature T cells. And it is assumed, and there was some evidence for it, namely that the external signal, here being Notch, increases as you progress through that particular organ. Okay, when it comes to this process, so here comes things in from the bone marrow. Here are the early stages. Sometimes they're called ETP, sometimes DN1. They go over to DN2A, DN2B, DN3A, and so on and so forth. Historically Christian as those. And these stages are defined by surface markers. So this is just surface markers. I have two questions today on different levels. One is the rapid proliferation that appears between things coming in from here until you reach DN2. There's enormous proliferation. It's between 1,000 and 10,000 of the 50 that went in. And you kind of wonder, how does that happen? Okay? Now, there are different options here. So I have my DN1 pre coming in, and this is my DN1 compartment. And you see I have partitioned the compartment into some subcompartments, neither of which have any we don't really know about, and there are no surface markers. We have surface markers for DN1, but it's clear that with normal division cell cycle times, that a lot has to happen, and it can be that you make asymmetric divisions here, that someone progresses to DN1 and the other one goes on and someone dies. So what we want to do here is just take the simplest model, and everyone has written down, we have seen a few compartment models already, I guess in Dr. Höfer's talk. So basically I want to see how does the rate of change for the DN2 compartment, when I made this change, depend on different ways that I can partition between commitment, which is green, and proliferation, which is blue. So I will model then the different commitments as a function of subcompartment in various ways. I would consider the death rates as constants, and I will fit to actually in vivo data. So in vivo data in this case is that you have donor cells corresponding to this DN1 pre, like thousands. You throw into the organ of the mice, and then you kill the mice day 1, day 2, day 3, up to day 14, I think. And then you analyze with these markers, the surface markers, how many there are at each stage. Okay. So it's a real in vivo experiment. Then we of course have some steady state knowledge, because this is a kinetic equation, so we're going to combine the kinetic equation with some steady state knowledge. Okay, so what kind of models could we imagine here? Well, if we start from the bottom, we can have a constant model. So there's a constant probability for each generation to fit the data best way. Now, within parentheses then, we have checked the constant probability for all possible numbers of generation within reasonable. And so the best fit here for a constant is with G = 11. You can have a linear relation such that you commit more and more linearly as you pass through the subcompartments. You can have a quadratic one, and you can have a geometric one, and you can have a go berserk and say only the last generation gives rise to commitment. So we have the data, and actually they go beyond 14, that doesn't matter. And you can see that whatever you inject, it goes down. And the DN1 also goes down because it's going to commit to DN2 where it goes up, and DN3 is down the line. We are only interested in going from DN1 to DN2, but we need to fit the entire spectrum for normalization reasons, because there is an injection there of a couple of thousand, and everything has to be balanced with that. So the model is just this factor, and we evaluate, as you all know, or you can realize, I have a lot of parameters. And then you have, as we saw yesterday, you have to evaluate your fit either by confidence limit or by the Ikaike criteria. For those of you who don't know it, is you have an error function, but that's not enough. You also add a penalty for, which is basically the number of parameters divided by the number of data points. So it's information content thing. We do this, and lo and behold, it's the last generation where it happens, or almost the last, with a geometric rise. So once you go into a DN1 department, you divide until generation something around, well, it's if we look at the geometric, around 8 or 9, and then you commit. So it's a rapid expansion, and you defer the commitment. So there are other parameters here. You know, you have things like cell cycle times, you have cell death parameters. They're all reasonable. I would say that come out of the fits, because that's another thing you have to check. So the whole thing I have summarized in this graph is that it's not like that you commit as you go along generation to generation, but you commit in the very end. So is this purely academic exercise? I would say it's not, because you need to get the numbers right out of your thymus for whatever we have discussed the other 2 days. And this is the initial booster, and it has to be pretty much right, giving rise to 10 to the 3 to 10 to the 4 DN2s. So one thing I haven't cracked, and I guess no one has, what's the underlying molecular mechanism? I mean, suppose one would go for this option where nothing, 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 everything. That would mean that you have a clock inside your cell that counts division, and someone has tuned it to 11. Doesn't sound, well, could be. The other option, of course, is that you have initially some protein which prohibits differentiation, and at every cell division you get less and less and less and less, and finally it goes. However, that would mean that the cells, no matter at what stage you are, you have to be able to measure differences of 3 orders of magnitude, because you're making that many divisions. So this is a problem. It's unsolved. And we go to the next sub-problem. And this is, when am I final with regard to making the decision to become a T cell? When is that final? And why? Okay. So, when did I start? I may have to skip something. Well, I know I have time, but okay. So now it's time for gene-protein interactions, and the objectives here is to set up a genetic network that characterizes T cell commitment. I will use genome-wide transcription data, a couple of years old, so they are not single cell, they are bulk data, and also extensive literature searches when it comes to knockdowns and overexpressions, and also recent binding properties coming from RNA-seq. Okay. Just a little reminder, normally when people do rate equations for small genetic networks, you use either Michaelis-Menten or Hill's function, stuff like that. I have to point down that I'm a physicist at some point at least. Namely, for all these processes, there is a very rapid process, which is the binding, unbinding of a transcription factor to a gene, and then you have the slow one, which is transcription, translation, and degradation. And for the binding, unbinding of transcription factor to a gene, thermal equilibrium makes sense, and you can write down, as a physicist would do, the partition function that things are on, and normalize to the sub-partition function that things are on and off, both on and off. Final expressions are similar to Hill's function, but it's a very nice gateway once you go into stochasticity. Okay, time for data again. So we have looked into what you want to do. If you want to look into commitment, you want to have a time series. We don't have a time series. What we have is, again, data that has been assembled according to surface markers for DN1, DN2, DN2A, DN23, and so on and so forth. So ETP here is the same as DN1. So somehow we have to convert these MTTs, medium transit times, between the different compartments to a time series. And there are various ways to do that. It's standard in engineering. And there are some key transcription factors. And for T cell commitment, 3 of them go up and the green one go down. And the green one is PU1. So PU1 should be, everyone knows it should be closed once you're a T cell. So it's good, it goes down. The other 3 are implicated for T cell maturation. So let's look at their interactions. So I collect everything I know from the literature and from binding experiments. And immediately, and also I add notch signaling to all the 3 guys that are important for T cell production. P1, it's a B cell guy, and these three here are known for T cells. And you can see there's a lot of mutual inhibition between these guys and this guy. So I have my rate equations derived, as I said, but this is not going to be a picnic. I mean, come on, I didn't have that many time points because I didn't have a real-time series. What I can say is that during this interval, if I look at all the other genes, they're pretty much flat. That doesn't imply that they're not collaborating here as cofactors, but at least they don't seem to drive anything. It's also a question, when you have interactions, like down here, you have three guys going into BC111B. Do they act with an AND rule, with an OR rule? And so, do they act as a dimer? We don't know. So it's not only a question of writing down a rate equation with all its binding parameters, it's also a question of which are these rate equations. For those you don't like math, most of you, so forget it. So this is how, for example, TC11B is supposed to vary as a function of, one example, as a function of itself, of GATA3, and then it's suppressed by P1. But you see, I put exponents here too. If such an exponent is 2, that means it's a dimeric coupling. If it's just 1, it's the normal. For notch, we know very little. What we have assumed is a sigmoidal gain function, and I think that that's not a big crime. Each core, you can see you have 10 parameters for each of these equations, and only the decay rates are measurable, not with an enormous precision. So, and here I throw up 2 other equations, don't read them. But we need to also include, like, do I have monomeric or dimeric bindings? And what kind of logics do I have? So I end up with 32 models, each with order of 10 parameters, and I have this lousy time series. You don't expect much, do you? But I'm continuing. So we have to reduce this search space here. So one thing is that this P1 and the other 3 govern different types, even though they suppress each other. So I make preliminary fits, Monte Carlo ones, while separately clamping P1 and the other one to whatever is measured, and then I model what's left. But then I can write down quite a few inequalities. For example, there are some reasonable constraints. Notch better be positive, right? It's an external force. That reduces the space. Decay rates have to be reasonable. And we put it somewhere between 10, I think it shouldn't be less than 20 minutes, and it shouldn't be more than a month. And as you do these reasonable things, you can do final parameter estimation. Now what is this? I shouldn't have boring tables, but I have it. So here are the 8 different options, whether you have and, or, and so on and so forth for the different logics here. Then in addition, is TCF1 or GATA3, are they monomers, are they dimers, da-da-da. We used both Kaike index but also 95% confidence limit in evaluating the fits. And these things here means that I survive 95% confidence. Now, the ones with an exclamation mark, those are the good ones, because not only do I have 95% confidence interval, but I also have even more reasonable parameters. reasonable big parameters that are kind of measured. So I have lowered that one. So I'm left with 4 solutions out of 32. Okay. Now, interesting thing is that all these 4 solutions that survive have GATA3 as a dimeric binding. Okay. And this is, at least, it's not a prediction in the world literature, but it's a prediction in my office, because I didn't know that before. And neither did my experimental colleagues. So now it's time for the big crescendo. And this is something that people in nonlinear dynamics are very interested in, namely how switches work. So you have an external signal, you increase it, and then all of a sudden you get an amplifier. And if that is sharp enough, that amplifier, you call it a bistable switch. Even more interesting is if I have an amplifier, like I seem to have here, and go up with varying the external signal, and then when I go down again, I don't retrace my steps. I go down here. So the switch remains on. That means it's an irreversible decision. So even when you pass further and there's no more notch or whatever external signal, you are a T cell and there's no one that can take you back. And I think with real data, may it be sparse, this is the first time. So we need to go to do single cells. We need to do single cells to understand the different compartments when we subdivide the DN1 going to DN2, and we do really need to do single cell understanding this commitment business. So as we learned yesterday, going from bulk data to single cell data is not only a question of getting more that you're not allowed to do bulk data because you don't have enough cells. It's also you can actually understand much more about the dynamics. And mostly in this situation, the deterministic equations, assuming bulk, that there are many copies of each molecules, you can use them down to quite few molecules, still being legal. Formally, of course, when you do rate equations, you're working with concentrations, and the formal requirement is that you have infinite amount of molecules. But infinity means different things. I mean, number of kids in a family, people tell me 3 is infinity, so it's context dependent. So we will just revisit the other questions, and then the questions I've been addressing, and we do 2 ways. We do RNA-seq on single cells with the new fluidine C1, where you can do genome-wide. And we use time-lapse microscopy in wells. We have 96 wells, and we investigate heterogeneity, notch level dependency, and also quorum sensing. Well, what's quorum sensing? Am I done? Quorum sensing are typically interaction between cells. Typically, it's very important in bacterial context where you have phase decision, stuff like that. I have a feeling that our quorum sensing effects here that may be more important than the notch environment, because it's getting more and more jammed as you go into the thymus. So what has been achieved here is, I have understood, I hope everyone else, deferral of commitment in the first passages through the DN1 compartment, and we have identified key players, and we are able to demonstrate that there is a decision that can never be taken back when it comes to T cell commitment. So this is done between me and a lab at Caltech, and we are geographically separated, but we are mentally in the same room. Thank you.
Thank you very much. So hi, I'm Yuval Hanati, and I want to first thank the organizers for inviting me. I'm working in Paris with this large group of people, well, some in Paris, some in Princeton, and I'm going to take you back to immune repertoires and tell you about some interesting things we are doing with them. So, just as a short reminder, immune repertoire is basically the diversity of T or B cells according to the receptors. This is a key strength of the adaptive immune system, right? This is a way the system can identify and respond to different threats. And we are trying to understand this diversity and research it through all its stages. So this is we like to look at it as a multi-layer process. So there is some initial production of diversity using in the VDJ recombination. Then there's some initial selection for T cells. It happens in the thymus already, for B cells not. And then there's some selection after they're activated by emitting a pathogen, becoming memory cells, and that interesting dynamics. And for B cells, there's also affinity maturation. And well, we heard all about that yesterday from Gu's talk. And basically, we are looking at all those processes in this kind of layers that they are based one on the other. And what's interesting that all of those processes basically are probabilistic processes. And so we model them as a theoretical group, but very much based on data. We model them as probabilistic models. So basically, we build a model and infer the model using the data and using maximum likelihood methods. And this way you can both describe the data and get some insight on the biological function behind it. So I'm not going to speak about everything you see here, but I'll give you a taste of some of the things we are doing. Repertoire generation, again, this is just a reminder. During the recombinations, there's different possibilities for V, D, and J genes. For instance, this is for, let's say, T cell beta chains or B cell heavy chains, and there's and there's choice from each kind of gene coupled with some insertion and deletions, which give the large diversity of possible immune receptors. And this is, as I said, a probabilistic process, right? There are different probabilities for choosing different V's, different J's, different numbers of deletion insertions, and there's no reason for any of this to be uniform or anyway arbitrary probabilities. So to try to infer that, we are taking a lot of data, and we only look for this point. We are sorting the data, and for this part of our model building, we're looking only non-coding sequences. When I say non-coding sequences, we actually mean that a lot of sequences that get produced during the recombination process are actually either out of frame or have stop codons inside the junction area, which is completely random, right? Those sequences cannot produce any protein, and thus cannot be selected. They're only there as hitchhikers on cells that actually have another recombination which was successful. This non-coded sequences give us a very good glimpse into the generation process because there's no selection pressure on them. And this was checked after the fact that this is indeed true. So basically the input here is a list of a lot of sequences, and not a list of sequences and not recombination scenarios. So we don't actually know what produced the sequence, right? We want to know what the probabilities for each V selection, insertion, deletions, and whatever, but we don't even have this input. All we have is a sequence. So what we actually do, and this I give like that. We assume some model, probabilistic model, with some factorization into probabilities, and we basically can learn these probabilities, probability of having certain V, probability of having a certain number of deletions given the V and everything else, using maximum likelihood. And it's slightly more complicated than just maximum likelihood because, as I said, we don't know the recombination scenario. So we have a lot of hidden variables in this kind of model. The entire scenario is a hidden variable, and we have to use the EM algorithm, which I'm not going to get into in this such short talk, but basically it's a mathematical way of being able to go through all the possible scenarios and learning those probabilities. And you have to understand something important here, that this is an assumption, right, this formula. It might not be true. So first model you try, which we actually tried, didn't fit the data. For instance, here you can see that the probability for V is decoupled from the probability of D and J, but D and J have joint probability because they're actually not independent. And this is something that was discovered during the building of the model. And this has a very good biological reason because of the place those templates are on the genome. For light chains, for instance, or T-cell alpha chains, when there's no D, there's actually a strong correlation between V and J for similar reasons. So eventually we get this probability for a given scenario, and the probability for a given sequence will be just the sum of all possible scenarios. And this gives us what we call the generative model. A model that gives probabilities for each generation of or each sequence to be generated. And this is a different model. It can be constructed differently for different compartments, different kinds of cells, T cells or B cells. The initial work, which was published in 2012, was on beta chain, T cell beta chains, and this was done on 9 different individuals, human data. And what was interesting is that it was pretty consistent between individuals. So different cells might have a different model, but between individuals, this is very similar. So although we are very different, our generation process is essentially very similar. Now, I want to get into a bit more details when I talk now about repertoire selection, which is everything after generation. So generation is some kind of baseline, gives you the basic probabilities for generating sequences. But what now is very important and very interesting is how the immune system basically selects the right sequences. So this starts already with what we call the initial selection. For instance, for T cell, it's happening in the thymus. So cells get created, but they get created with this random process that produces a lot of cells that even if they are in frame and everything, might not be good receptors at all, might not fold correctly or anything like that. And we can imagine those, and we know that there is some kind of selection on that. So we're trying to quantify the selection. We can actually see the selection very easily if we just look at the length distribution before and after this initial selection. So the blue curve is length distribution. This is CDR3 length, right? So a very specific variable area in the receptor, in the TCR in this case. And the distribution before selection, the blue line, you can see it's wider and longer than the distribution after selection, which is the black line, which basically means that selection had done something specific, and it doesn't seem to be blind, right? It doesn't choose some sequences not according to anything, but chooses specific sequences. And we wanted to try to quantify this in a more general way, and find out which factors makes the sequence good for selection or bad. So the idea is to exactly do this kind of comparison between before selection and after selection. So we define in a very general manner a selection factor for each sequence. The sigma is a sequence, and there is a probability of generating the sequence and the probability of seeing it after selection. And the ratio between those, this we call Q. All right, this is a very clear definition that is per sequence. The only problem is there's no way to measure this factor, right? Because we don't, sampling-wise, we don't have any way of really sampling the post-selection probability. Generation probability, okay, we know because we build a model for that. But we don't have yet a model for post-selection, so basically we need a model. The model gives another very important feature here, and it's important to understand that we're not building models just because we can measure. We're building models also to learn biology. And in this case, we want models that gives the selection features of the sequence, because that's what we're actually interested in. So this is the kind of, so let's look at the sequence. Let's look at the CDR3. So the CDR3 has a specific length. Each sequence will have a different length. And there is the amino acid content of, you can see here, amino acid content of, this is for instance length 8. So this is an amino acid. So the actual what amino acid, and there's what were the V and J's that actually produce this sequence. This CDR3, because some of that is actually outside of CDR3 and might affect selection also. So these are the factors biological features we assume to be most relevant for selection, and then we can actually write a model. So this is a model we're actually using now. So basically we factor the selection factor into different factors for the length, for the identity of the V and J, and for the amino acid content, all multiplicative. Again, as I said before, this is an assumption. We have to build this kind of model and check if it works. Spoiler, it works. But we actually, you can see that even here we assume that in the amino acid content, it's independent, the selection factors, right? It gets selected from each position by itself, and we actually tried also a bit more complicated models with a correlation between neighbors, and it did not improve the model much. So this is basically a model, and now we just have to study it, to basically to learn those factors, and now I'll get into a bit more details. So how we're actually doing it. So this is the outline. So first we do some pre-alignment. So the pre-alignment basically is saying which V and J's are actually possible for each sequence. So we're not taking the best V and J possibilities, because we actually believe that this will bias our distribution, because you cannot really know for certain which V and J were used to create a given sequence, and this has a few reasons, both because of sequencing errors, which are always almost there. Now the data is much better, but still there, and then the V and the J are actually very similar to each other. The different V's are actually very similar to each other, so a probabilistic method like this that actually gives a few different possibilities for V and J's is essential. So we do some pre-alignment, and then we have a list of possible V and J's and how do they align. And then we choose some initial models, so some values for those parameters, and we're trying to calculate the likelihood of the data given the model and maximize this likelihood. So we're saying, what is the probability to get the data we see using this initial model, and then what can we do to the model to maximize this likelihood? In practice, what we're doing, if you work out the math, which again I'm not going to do here, is we are calculating the model-dependent marginals. So we actually calculate, let's say, how many times out of the model and specific amino acid appeared in a specific position or will appear given the model, and then we compare it to what we actually see in the data. And then using this difference, we can modify our Q values, the parameters of the model, to make this difference smaller. And this will actually maximize the likelihood. So this is an iterative procedure. In a sense, it's again more complicated because we have hidden variables. We don't know, as I told you, we don't know which V and J were used. We only have possibilities, so we actually have to run over different scenarios of VNJs, and using again the EM algorithm, the expectation maximization algorithm, and thus basically learning the parameters one by one. And eventually, when this procedure converge, you have to check that you get a good model. So I'm not going to get to all the way we do it specifically, but the idea is to learn the model on different subsets which are independent and see if they agree, and also see if the method can predict things you didn't put in. So in this case, we put into the as data we use only the frequencies of amino acids in different positions, but we can check, for instance, if we get the 2-point frequencies of amino acids correctly, and we do. When we have the right model, we do. So this is very this is a very good validation. Also, this was done for the same data set as I said before, of 9 individuals T-cell data, but this time not for the node coding sequences, but for actual coding sequences, right? Because we want to know what actually was selected and not just generated. And between the 9 individuals, again, we got very similar results. So I'm going to show you some results now and show you what's so nice about holistic models. So for instance, yeah, that's a lot to take. So I'll explain. This is basically the selection factors per position, per length of per amino acids. So this is for T cells, and you have 20 plots here for the 20 amino acids. The x-axis, the horizontal axis, is a position. Okay, so this is position 1, 2, 3, 4. It's too small to see, but believe me, those are running numbers. And the vertical axis is a length. All right. So we give different selection factors for different lengths. So position 1 or position 5, let's say, for sequences of length 8 is not the same as position 5 for sequences of length 12. And you can see here why. So first of all, this is results from the 9 individuals. This is average over all of them. So there was very similar pattern, and you can see here different patterns. There was a very similar pattern for all of them. So even averaging over all, it did not disappear. It actually, we got to see it more clearly. And you can see that, for instance, in the places I circled now, there's some selection. So, okay, I just explained the colors. Anything red is actually selected for. So this amino acid in this position makes the sequence more likely to be selected. All right? While blue makes the sequence less likely to be selected. Okay? So for instance, if we look at alanine, which is the first amino acid here, it's positively selected, but only when the sequence is long enough. All right? But when the sequence is short, it's all blue, but it becomes red only when the sequence is longer. And there's other amino acids which are similar in this retrospect, but other amino acids are just generally selected against, especially histidine and zinc. And but more interestingly, in this plot you can see actual edge effects. So remember, the edges are very important here because what actually lies, the way the CDR3 is defined is by conserved regions just on the ends, right? So there's a cysteine on the V side and I think a phenylalanine or tryptophan, I always forget, for T cells on the J side, and those conserved positions are actually have conserved amino acids, and probably close to them, it makes sense to have a specific amino acid or not to have specific amino acids. So we can actually see that glycine is very much selected in a place just before the last. The last is also okay, but it's most selected place before the last, which basically tells us something about this position. And this is again, as I told you, a very stable pattern. And there is, I'm not going to get into it, but there is you can do some kind of analysis on the properties of the amino acid, then you'll see that there's certain reasons certain amino acids are selected or not. But this is something extra. We done the same thing for B cells, initial selection. So this is not timers, and they are longer. It's heavy chain in B cells, and you also get a pattern. This is of course less individuals because we had less individuals in the data set, but much more sequences for each individual. And again, you see similar patterns, but different, of course. So this is already quite interesting, but what we like very much about probabilistic models, it gives you a way to analyze diversity. So we, as good physicists, look at diversity in terms of entropy. So for instance, for B cells, if you see here, the recombination events, which we have probability distribution for, we can say it has a diversity of 74 bits, all right, 2 to the power of 74. This gives you the approximate diversity of all possible ways to construct a sequence. You can see the breakdown below here. It's mainly because of insertions, right? So actually, gene selection is a small part of the diversity. Now, if we look at this recombination event, this is not the entropy, this is not the diversity of the sequences, because the sequences, there's a few ways, different recombination scenarios to produce the same kind of sequence. All right, so this is we call recombination, convergent recombination. So it goes down to 70 bits, 68 bits if we just look at sequences which are productive. So we exclude all sequences which are produced with out-of-frame recombination. But still, if we compare this productive sequence entropy, 68 bits, to the post-selection entropy, so we actually look at our model after selection, it has 10 bits less entropy. So it basically means there's a huge reduction in diversity. All right, selection is not blind, and it means that actually, if selection was blind, selection would choose sequences randomly. We will basically see the same kind of diversity, but diversity goes down a lot. We can see it also in T cells. Diversity goes down from 43.5 to 38 bits. It's a tenfold reduction in diversity, while we know that okay, this got weird, but we know that timing selection keeps 50% of the sequences. So it basically favors, it gets rid of rare clones. So clones which are produced during generation, which had a low probability to be generated, actually have also lower probability to be selected. All right, selection favors clones which are more likely to be generated. We like to say that selection anticipates, that natural selection anticipates somatic selection. So it kind of makes sense. You can see it here in the plots for the distribution of the probability of generation. Again, before selection, it's the blue plot. After selection, the red plot. It shifted to the right. This is a logarithmic plot, so it's actually quite a shift. So basically, we see more probable sequences after selection. You can also see it from a direct correlation between the probability of generating an amino acid in a position and the Q factors, the selection factors. And if we look at the correlation coefficient, this is a distribution of them over all possible positions. It's very positive, and basically, and it makes a lot of sense that the system, our system, have evolved in a certain way that it doesn't waste too much. It has to produce a huge diversity as a baseline for protection, but it doesn't spend too much on sequences which are not likely to get selected. So this was very interesting. Another result we saw. So this model is very general. It can be run on amino acids, but it can run on codons in the same way. So instead of having 20 amino acids, we'll have 64 codons generally, but it's quite the same as part of the model is working. So we can, in this plot, you actually see there's 12 plots, one for each position for sequences of length 12 only here. This is T cells, and the blue circles are the selection factors for every amino acid. So this is the horizontal axis is amino acids, and the red crosses are the results for the codons that fits this amino acid. And you can see that the codons usually go very well with the amino acid. So selection is actually on the amino acid. So we're talking here really about functional selection and not something that happens on the way, the RNA level or something. It's something that is functional on the peptide itself. All right, and it only breaks down a bit close to the end because of small number effects due to the low diversity because of this is the area of basically the J or the V gene, the diversity goes down. So everything I said until now was on initial selection, was basically on naive sequences, so naive cells that have never met any pathogen. And we're starting to look also on memory cells. So on T cells, we actually haven't seen much difference between memory and naive cells, and there's different reasons for that. I'm not going to get into. Just I want to, before the end, I want to tell you something we've done with B cells, which is rather new. And we try to look at somatic hypermutation. And there we can also, so we heard about affinity maturation yesterday, and this is the fact that you get some amino acid, some nucleotide mutations on B cells. And we wanted to try to understand, the baseline profile of those kind of mutations. And this is already clear for non-coding sequences, because also non-coding sequences get those hypermutations are just not selected. So we can really look at the mutation profile without looking at the selection of those cells data, which are heavily selected, right? And we found that it captured by a model error rate predicted by a 7-mer context model. 7 is a nice number. And you can see the model here. So this is basically kind of an energy model, right? So the probability goes like the exponent of some factors, and you can see that it's really very much dependent on the entire context. So 0 is the place you're going to get the mutation, and you see it's very much dependent on the nucleotide next, right after, and also quite a bit on the one before. And this kind of model we built out of data again, the same kind of way, using some kind of EM algorithm, and you can see it tested in front of data. So this is the position on the V gene, all right? So this is the CDR3 is here somewhere. This is the V gene, and the blue plot, the blue line is the actual hypermutations we see across all sequences, and the green plot is actually our model, and it fits very nicely. We also checked it on some of the data to see we are not overfitting here, and this is a correlation between those points. So it's quite nice that you can fit this kind of model and get the baseline, basically hypermutation context. Then you can build on it later the selection. But as I'm running out of time, I'll just conclude. So I showed you the probabilistic processes called probabilistic models, and probabilistic models have the advantages. For instance, we gave us a way to use statistical inference to in disentangled generation selection. We can see those effects differently. We saw universal selection fingerprint stable over individuals. We saw the generation dissipate selection. And we saw that the diversity of repertoire is significantly constrained. This is very important because we actually want to study this diversity. And we see that while diversity is good, it can also be something bad. And we also now showed you some results on memory cells, and there's many continuation of this work, both on more selection processes that I saw I showed earlier, and on different kinds of model organisms and kind of cells. That's it. Thank you.
Thank you.
Thank you. Dear Chairman, dear colleagues, ladies and gentlemen, I will be the third guy who will talk about bioluminescence, but I'm the first one from Moscow. Sorry about my Russian accent, and excuse in advance my English. So there is only one. I'm going to, as I mentioned, I'm going to talk about bioluminescence investigations, optical imaging, and there is only one thing connecting me, my work, with the topic of the conference. It's the word modeling. I will talk about animal models of tumors and other diseases. But first of all, as far as I first guy from Moscow, I'd like to show you some images according current political situation. Moscow is a beautiful city. Don't be afraid to the newsmakers, and welcome Moscow. And don't be afraid. Sorry. Okay. Here is our university, Pirogov Russian Medical University, named by famous surgeon Nikolai Pirogov. Here is our team, our big boss. And let me to introduce our medicinal nanobiotechnology department. We got some facilities for in vivo studies. For example, we got MRI, in vivo MRI system, 7 Tesla. So we could investigate rats, small animals, with almost histological resolution. So you could see brain and the body. And we have some models of disease. For example, we got the model of stroke. And you can see here in diffusion image 1 hour after occlusion of internal carotid artery, you could see changes in diffusion image, but you couldn't see this one on T2 images. So early diagnostic of strokes, but after 24 hours, you can see the stroke in T2 images. So the stroke model, we use DTI, it's tractography for reconstructing neuronal pathways. We got spinal cord injury. You can see a cyst inside spinal cord. So we use tractography. We reconstructing neuronal pathways to quantitative assessment of the damage of the lesion of spinal cord. So, and we got some tumor models, and I will talk about tumor models. So we have got glioblastoma multiforme in rats using C6 cell lines. It's high-grade glioma. So you can see huge glioma here after 24 days after stereotactical implantation. We used in our work the model of multiple sclerosis. You could see demyelinization here on diffusion. And this picture only for aesthetical reason. It's a beating heart of mice. The rate of mice heart is more than 500 rates per minute, so it's rather difficult to reconstruct such images. And now at the time for optical tomography or optical imaging, we use iris spectrum CT with micro CT and fluorescent and bioluminescent detection. So we could use 2D bioluminescent detection and 3D reconstruction. Here you can see a glioma inside the brain. And now I'd like to show you some data obtained on a model of breast cancer. As you know, breast cancer is a very severe disease with a lot of metastases to the brain, to the bones, and rather difficult to treat such metastases. So we produced a model using 41 cells obtained from ATCC, and we modified those cells with a vector with a gene of luciferase and with a red fluorescent protein. So here is the final stage of the tumor, and we use micro-CT to do 3D reconstruction. In this reconstruction, we could measure the volume of primary focus. And here is some interesting results of volumetry of carcinoma focus. So here is a wild type of 41 cells, and the volume on day 20 is 500, on day 28 1200 microliters. So modification with luciferase gene almost twice decrease the volume. So, but the interesting thing is that modification with red fluorescent protein very severe decrease the volume, the tumorigenicity and the proliferation rate. So it's occurred because of immune reaction to the red fluorescent protein, and you can see on survival curve that about 20% of mice survive. So this model is not so good for preclinical investigation, but using luciferase gene, it's okay. It's the survival curve doesn't so differ from the wild type 41 cell, and this model is useful for preclinical study. Here you can see MRI scanning of carcinoma, 41 carcinoma. So the primary focus does not accumulate gadolinium, is the MRI contrast, and as well as it doesn't accumulate fluorescent dyes like protoporphyrins, allocenes, and etc. So it's rather difficult to trace metastasis. And here you can see metastasis. You can see metastasis on lymph nodes, on intestinal, and in brain. This carcinoma produced metastasis in brain. About 10% of mice demonstrated brain metastasis. So now we are working in obtaining the clone which could preferentially metastatize to the brain. So one more MRI scanning. You could see lymph nodes bearing with metastasis, and this is one thing I'd like to put an accent. So we use a so-called apparent diffusion coefficient for estimation of for example, antibodies efficiency, antibodies treatment efficiency. So as you know, such type of drugs like antibodies and other recombinant proteins with anti-tumor activity couldn't produce the decreasing of volume of tumor volume, how to say, very quickly, but they accuse some changes in tumor tissue. So they could produce inflammation, cell infiltration, and some other changes. So we could detect it. We could detect these changes using diffusion coefficient. So it's some kind of measurement which we measure just the dynamic of water diffusion inside the tumor tissue. So, and we could get some interesting information. For example, doxorubicin treatment decrease the diffusion coefficient, and such treatment as treatment by Resorba and the recombinant protein, anti-tumor protein lactaptin increase the diffusion coefficients. So we could use this data for the analysis. And as I mentioned before, one of main problem of breast cancer is bone metastasis. So we spent some time to make an algorithm to detect bone metastasis. So here you can see bones. In this movie you can see the resolution of micro-CT. It's rather good. You could see a vertebra. It's a mice. And here you can see the metastasis into a vertebra. We designed some measurement for quantitative assessment of metastasis, bone metastasis, using Hounsfield scale. As you know, it's routine X-ray scale. The density of air is 0. The density of water is 1000. So we could use this scale for detection of metastasis. So we could mark a volume and measure the density. And here is an example. You can see right knee gave us 1.4 Hounsfield scale, and the left knee 4.0 Hounsfield, and the resolution, the verification with high resolution micro-CT revealed the metastasis in the left knee. Here you can see this metastasis. So we could quantitatively estimate such metastasis. In this movie you can see the metastasis of the osteolysis here. It's rather high resolutive, as I said. So, and 3D optical imaging provide us to make a quantitative assessment of a primary focus of carcinoma. So, as you know, and that it was already said here, that luciferase activity needs surviving cells. So the light from tumor means that the tumor is still alive, and we could get some quantitative data. So here you could see we could estimate total flux during the tumor progression. We could estimate average radiance, and we could estimate area of luminescence. So of course we use this data for our preclinical investigation. But of course the main idea of such modification with luciferase gene is to detect metastasis using bioluminescence. But it's rather difficult if you got the primary focus. I didn't say that we used orthotopic model. So we inject carcinoma cells into breast fat pad of mice. And it's rather difficult to detect metastasis if you got a bioluminescent primary focus. It looks like we can't see stars at day because of sun. So the idea was to screen a primary focus or to delete it, to reject it. And after that we could use high exposure and we could detect metastasis. And of course we were interested what's the sensitivity of our detection, how many cells into metastasis we could detect. So here you can see metastasis into lungs and into bone. So in vitro we estimated how many cells we could detect. So we could differ light from 18 cells from 8 cells. 16 cells from 8 cells. But it's of course it's a data in vitro. In vivo it's much more difficult. So we tried to calculate it. So it's no problem to detect more than 1000 cells. I mean, even in deep metastasis, such, for example, metastasis into thorax, into lungs. So we could detect more than 1,000 cells. So, and let me show you. Here is a metastasis into knees, bilateral. Here is some smaller metastasis, but we could detect it. And here is a huge metastasis, and we could verify it using micro-CT. You can see the osteolysis. One more mice with rejected primary focus, and you can see metastasis in lung. It's rather big metastasis. And of course, we could verify such big metastases using MRI. But these two small metastases we can't see via MRI. So this method is better than MRI, even 7 Tesla MRI. Of course, we verified our data histologically. You could see high-grade tumor, it's 41, into lungs. And as I mentioned, some metastasis more than 0.1 micrometer, 0.5 micrometer, we could verify it using MRI. Here you can see the metastasis in MRI and with bioluminescent detection. But as I mentioned, such metastasis we didn't find it on MRI data. But the problem is, of course, the metastasis into brain. So brain is screened by skull. How to say chair? I mean bone. Yes, skull. So it's rather difficult to measure bioluminescence. So, of course, if, as I said, if the metastasis is more than 1,000 cells, we could see brain metastasis or intracerebral metastasis. But and we could verify that using MRI. But if the metastasis is small, you can see here it's just the initial level of brain metastasis. We've found this. Here you can see it's just a perivasal infiltration of carcinoma cells. You could, it might in these slice maybe 50 cells. So it's rather small metastasis. So we couldn't, of course, detect such small metastasis using our bioluminescent detection. So it's the limitation of optical tomography. And now, what therapeutic approaches we used finally for what everything is. So we are working with oncolytic viruses. Someone calls oncolytic viruses as a magic bullet. About that, it's the term of Paul Ehrlich. Of course, you remember he thought about magic bullet, and he discovered a blood-brain barrier first experimentally, but he didn't know that he discovered it. So we used oncolytic viruses. We used anti-tumor antibodies. And now we started together with our collaborator. We are going to start some immunotherapy and DNA vaccines using this model. So this model is quite useful for such investigation. So as an example, I would like to tell you about our results with connexin 43 antibodies. You know that connexin 43 is the main protein of gap junctions. Our group and some parallel group revealed that the gap junctions gap junction formation play some important role into invasion of tumor cells, especially into intracerebral tumors like a glioma. and like brain metastasis of carcinoma cells. So we cloned the second extracellular fragment of connexin 43 and produced monoclonal antibodies. And these monoclonal antibodies could detect it's the staining of living cells, and after staining cells were fixed. So you can see connexin 43 on living cells. It's glioma cells, and here is our glioma model. Some histological results, and I like this picture because I always show these pictures to our neurosurgeons in our clinic, especially to those neurosurgeons who believes that they could treat glioblastoma surgically. It's just impossible. You could see here is a primary focus, and here is like a tree. Here is an invasion strains. So it's rather difficult to treat such tumor, to reject. It's impossible to reject such tumor completely. So we revealed that in this peritumoral zone occurred a huge expression of connexin 43. Of course, partially this expression occurs because of reactive astrocytes. You know that in this picture, red is GFAP, it's reactive astrocyte. Here you can see. In this picture, green is astrocytes of astroglial bank, peritumoral bank. And you can see connexin 43 in astrocytes, but also you can see some GFAP negative cells into astroglial bank, which are connexin 43 positive. And we demonstrated, oh sorry, I will come back to these slides. We demonstrated that those cells, connexin 43 positive cells, are glioma cells. So we labeled glioma cells before implantation using DI. We could see DI after 3 weeks post-implantation. So, and we injected our antibodies intravenously to the rat. And here, I will zoom a little bit. Here, DI positive cells. So here is a glial bank. It's almost healthy nervous tissue. Healthy, of course, it's not completely healthy, but it's outside of glioma. So, and these cells, as I said, DI positive. So that's why we call these cells glioma cells. And these cells accumulate antibodies injected intravenously. So, let me return. Here is the results of our preclinical study. Sorry for some Russian words, I will translate. So here is days post implantation, and here is a treatment of antibodies. Here is a control group. You can see that you can see huge glioma since the 3 weeks post-surgically, post-implantation in control group. And 20% of group of rats which were treated by antibodies to connexin 43 survived. So here is a Kaplan-Meier surviving curve. You can see twice time increase mediana, and you can see 20% survived after such therapy. So it's rather interesting results, and we believe that we could repeat such results, not even in red glioma model, but in primary gliomas, in immunodeficient animals. So we revealed that our antibodies inhibit the heterological gap junction formation. So that's why we hypothesize that our antibodies prevent the invasion of glioma cells, blocking gap junction formation, especially heterological gap junction, because glioma use astroglial astrocytes. They use it like monkeys use trees. I could see it in my microscope. So our antibodies block such gap junctions, and that's why we demonstrated it both in vitro and in vivo using fluorescent confocal microscopy. So here is target cells, and we could reveal it. And now I think the next step of our study will be the immunological research. So thank you for your attention, and I'd like to thank organizing committee for the opportunity to see this beautiful place. Thank you very much.
Good afternoon. Thank you very much for having the chance of being here, and thank you for staying for the last talk, which is also not quite completely fitting into the program, but it fits at least subject-wise to my previous to the previous talk. So we looked into immune phenotypes of patients with glioblastoma multiforme in patients, and the immune phenotyping gave a hint that certain cells of the immune system play a role in letting these tumors grow. Now we have a collaboration with the neurosurgical department, and we deliver our immune data to the department. Although they were not immunologists, they were not at all interested in that for 2 or 3 years. But finally they are, and we get tumors regularly within a study, so that makes things easy. The background, you already heard about that. GBM is the most common primary malignant brain tumor. It's restricted to the central nervous system, where it also metastasizes. But we have data that the peripheral immune system recognizes the tumor, and that is in part due to the circulating tumor stem cells, and there is a recent publication which demonstrated that they are quite frequent. Now the idea we have is that in the brain that there is this massive tumor growing, that this tumor, at least in humans, I don't know what the animal models, is infiltrated by immune cells, most importantly by macrophages, the two so-called tumor-associated macrophages, sometimes also some lymphocytes, and this is data from immunohistochemical results, and these immune cells appear to release some cytokines which are detectable in the peripheral immune system, and the tumor also is likely to release tumor stem cells into the periphery, which activate the immune system or inactivate it. Now you get the resection of the tumor once, and you have a chance to look into tumor-infiltrating macrophages, but in the rest of the time you are left with the peripheral immune system. And that's what we looked at. So we have data now from 53 patients analyzed. So we have about 100, which we looked in. Mean age is 57 years old, some very young ones, and it's all glioblastoma type 4. So not the ADH1 positive ones, and all these patients undergo surgical resection, radiotherapy, chemotherapy with the Timodal regimen. We compared the immune phenotypes with 36 donors, which just got quite some bias because some of these donors were younger than the patient, but it's hard to find healthy older individuals, at least in a hospital where we are, which is a surgical hospital, and you always need ethical commitment, ethical improvement. So we looked into this peripheral immune system using flow cytometry, using a flow cytometer software, and we analyzed our immune data by mean fluorescence intensities, that is the density of immune active molecules, as well as percent positives from the leukocytes. In addition, we look for certain plasma biomarkers, and we only use the so-called Siemens assay, which is a validated assay, and you can use it also for clinical diagnosis. and I will show only a few of those today. Statistics is Mann-Whitney test to compare groups, and the Kaplan-Meier curves have been used to compare the data with survival. Now, when you look into biomarkers which have got something to do with inflammation, like IL-1 beta, or anti-inflammation, like IL-10, you see that the median of the patient group is lower as compared to the healthy ones, but this is not borderline significant, although there are some exceptions in both groups. And for the IL-10 it's the other way around, so levels and concentrations are higher in the patient as compared to the healthy controls. And this is quite an interesting marker. It's got something to do with inflammation from the macrophages, and the plasma ferritin is increased in the majority of the patients. And this is a marker for T cell activation and also for activation of matured dendritic cells. It's the alpha chain of the IL-2 receptor. There are some differences, but they are not significant if we compare the median. So this is how we do our immune phenotypes. You may be familiar with that. So this is the scatter analysis, which shows you the lymphocytes, monocytes, and the granulocytes. And what you can do, you can compare these scatters in addition to the marker profiles for every patient, and you can also do follow-ups. What I would like to mention is that here the lymphocyte population appears to be the most important one. So we have many patients who have almost no lymphocytes, and you can, if you look close enough, you can also see that this individual, for instance, has more activated and cytotoxic lymphocytes because the scatter in the y-axis, that is the 90 degrees scatter, is higher. Now, when you look into CD3 expression in the lymphocytes of the patient and you compare it with the healthy donors, you see that patients have a median less CD3 positive lymphocytes. Some have really very, very few. That is what doctors don't look for. So they just look for the leukocyte count. They look okay, but this patient is really severely immune deficient. And when you compare this with the expression density of CD3, the difference is even more remarkable. So these patients have tumors. They are investigated on one day before surgery, and the immune system recognizes this, and then we think that the reduction of the CD3 as well as the T cell receptor, which I'm not showing here, has got something to do with immune function of these lymphocytes. And CD3 coordinates proliferation, cytokine secretion, and also differentiation. Then I would like to emphasize another marker, which is probably much nicer than markers like CD4 and CD25 to define and identify regulatory T cells. This CD39 molecule is a so-called NTPase. It can degrade ATP, and there is an increased expression in the patient as compared to the healthy donors, both in percentage and also in expression density. And this marker has been recently looked into the tumor itself. So we take fresh tumor's tissue and we dissect it and look for CD3 expression, and we find CD39 expression, and we find CD39 positivity. Now at this point I would like to link this specific immune system guided by CD3 and T cell receptor with a so-called innate immune system. And the CD39 is the linker molecule because it degrades ATP, which is one of the major trauma stimulus in tumors as well as in other traumatic diseases. So ATP can be released from erythrocytes and from any diet tissue, and this is a so-called traumatic stimulus. The essence of trauma: cell damage and lysis, free DNA, and which the free DNA can be recognized by toll-like receptors and also other receptors inducing inflammation, and lead to the activation of pro-IL-1 beta and the transcription activation of NF-kappa B and transcription of pro-IL-1 beta. And that is processed by the inflammasome in the moment when the ATP, which is also released from damaged tissue, binds to the P2X7 receptor. This is a cholinergic receptor which leads to calcium influx, and this calcium influx finally activates the inflammasome to produce IL-1 beta, which is one of the major stimuli. And this IL-1 beta brings you into a state of inflammation, which we tried to find in these patients, but we did not. We did not find increased IL-1 beta. We know there is a reason for it, because we might know that whenever a patient is diagnosed with glioblastoma, he gets a lot of steroids, very high dose. So we didn't find this, but we still think that this mechanism is active. And binding to ATP leads to activation of the P2X7, as I said before, inflammasome activation in macrophages. And if that happens in T cells, the T cell goes into apoptosis. And there's only one way how to escape this by the T cell, if it expresses CD39, and this CD39 is able to degrade the ATP and generate AMP. And there is another molecule, another NTPase, which works in addition, and that is the CD73. And that activates the generation of adenosine. And adenosine is then able to bind to the adenosine receptor and downregulate this T cell receptor mediated stimulation. So that is a context which brings together the innate immune system, that is the trauma, the ATP, and a marker which is new in the field, that is CD39, which is increasingly expressed in regulatory T cells. And we all have problems to identify these Tregs with markers. You can use FOXP3 and do transcriptional analysis, but this is much easier, and there appears to be a clue in glioblastoma. Then we took all these 52 markers we looked into, and we draw these Kaplan-Meier curves, and we found that patients who had an extremely short survival time had a decreased amount of CD8 positive killer cells, whereas those who had increased killer cells had a better survival, although significancy is not really convincing. Also, CD8 is different between patients and healthy donors with both percentage and expression density. And there is another combination which is very interesting, and we haven't talked about that during the last 1.5 to 2 days, and that is activated natural killer cells. They respond and kill tumors which are deficient of MHC class 1 and class 2. Or class 1 is important, and the glioblastoma is in most cases class 1 negative. This is also extremely related to survival, so those patients who have only few or non-detectable activated NK cells have an inferior survival, at least in this first time. So we don't know what happens in that one. Okay, again, differences between patients and healthy donors. And in my last 3 slides, I would like to show you something which was new to us. We do, in addition, imaging, but not with an MRI, but we use freshly established tumor cell lines from patients, and we use the same patients' NK cells and killer cells and look for interaction. Now the killer cell has on the surface these microvilli, and then it makes contact with the tumor surface, which looks different, and all tumor surfaces look the same. So although the markers may be different in different patients, but the surface looks the same if you use scanning microscopy. And then this killer starts to kill and makes an interaction with the target, and the tumor doesn't like it. And that's what you can recognize by making these blebs in the area where the killer cell binds. And when you follow the killer cell by just putting some color on the microvilli from the killer, and leave the surface of the glioblastoma in gray, then you see that these microvilli sometimes go through. And here's an area where the microvilli don't look so nice. If you take a similar image 1 hour later, then you see that the killer cell starts with apoptosis. That means the surface is not villous anymore, it's more smooth, and these protrusions retract. And here the killer looks even in a worse shape, and it's completely different from other killer situations when the killer cell makes a direct contact. And in the end, and that is pictures I'm not going to show you, this killer cell is phagocytosed by the glioblastoma. And we have no idea what kind of receptors are involved, but they must be different from other receptors recognized by tumor cells. So I would like to leave you with this and summarize. We found a diminished expression of CD3 epsilon density, which is related to a selective upregulation of myeloid-derived suppressor cells. and probably the activity of CD39. And with this last image, I'd like to show you those cells which are also found in the tumor. That is not only lymphocytes, but also this cell type. These are all monocytes or macrophages, and if you type them for markers, they have a high CD33 and a high CD15. There's one poster outside also emphasizing the importance of CD15. And there is also a funny interaction of these tumor cells with these MDCs. So they make contact, and the contact antigens we also don't know. And we wonder whether these connexin 43 play a role. And the last point I would like to make is that CD16, CD56 positive cells do have an anti-tumor activity, but that does not appear to pertain for a longer time, neither in vivo nor in vitro, and in these 2 hours. So the interacting molecules will be kind of interesting, and I'm looking forward what you will bring out in your whole animal model. So thank you very much. This is the group being involved, and the person doing most of the work is Hawa Mostafa. She's from Lebanon, really very motivated student, which also makes contact to neurosurgeons, because we need the neurosurgery, we need medical people in order to get our research ongoing. Thank you very much.